Not long ago, researchers achieved something long regarded as nearly out of reach. They produced a genuine photograph of a planet located in a completely different star system. This wasn't a painting based on data, not a computer-generated mock-up, but an actual image built from light that had physically traveled across the galaxy to reach us. To grasp why this matters so much, it helps to look at the current state of exoplanet research. Astronomers have now confirmed close to 6,000 planets existing beyond our own solar system. These worlds vary wildly. Some dwarf Jupiter in size, others are smaller than Earth, some are rocky, others gaseous, and a few even orbit pairs of stars simultaneously, circling two suns at once. Yet out of this enormous number of confirmed planets, the overwhelming majority have never actually been seen, not photographed, not directly observed in any visual sense. The explanation lies in how most of these planets were found in the first place. Picture standing in a completely dark room and trying to locate a lamppost by watching for a person's silhouette, briefly blocking its glow as they walk past. That's essentially the logic behind the primary method astronomers use. They monitor a star's brightness over time, and if it dims slightly and periodically, that's taken as evidence that something, almost always a planet, is passing in front of it. This is called the transit method, and it has been responsible for the vast majority of exoplanet discoveries to date. But notice what it never actually does. It never lets you see the planet. It only reveals its shadow. This is exactly why the recent achievement of the James Webb Space Telescope stands out so dramatically. Rather than relying on a dimming shadow or an indirect wobble, Webb captured actual light emanating from the planet itself. A direct photograph, not an inference. And remarkably, this newly imaged world now holds the record as the lightest and smallest exoplanet ever captured through direct imaging, surpassing every previous benchmark in that category. The planet has been given the designation TWA-7b, and it circles a young, dim red dwarf star known as TWA-7, sometimes referred to by its other name, CE Antlii. This star system sits approximately 111 light-years away from Earth, within the constellation Antlia. While that distance sounds unfathomably vast in human terms, on a cosmic scale, it's almost negligible. Essentially our galactic neighborhood, especially when compared with a universe that spans tens of billions of light-years. What makes the host star particularly compelling is just how young it is, estimated at somewhere between 6 and 12 million years old. For context, our own sun has been burning for roughly 4.5 billion years, making TWA-7 an infant by comparison. Because the star is still so new, it remains encircled by an expansive disk composed of leftover dust and rocky fragments, raw material that never got consumed during the star's formation and hasn't yet coalesced into fully formed planetary bodies. Earlier observations conducted from ground-based telescopes had already revealed something unusual about this surrounding disk. Instead of forming one continuous ring, it was structured into 3 separate bands, with visible empty gaps between them. In the field of planetary science, such gaps typically signal one specific thing. Something with enough gravitational influence has swept the surrounding material out of its path, essentially carving a lane through the debris. For years, this observation led scientists to strongly suspect that a hidden planet was responsible for shaping the disk in this way, even though nobody had actually managed to spot it directly. Detecting a planet nestled inside a dusty ring, sitting extremely close to an intensely bright star, ranks among the most technically demanding challenges in modern astronomy. It would take a combination of cutting-edge optical engineering and extraordinarily careful data analysis to finally confirm what was hiding there, setting the stage for exactly what happened next. To understand exactly why photographing a planet is so technically difficult, imagine trying to spot a single firefly hovering right next to an industrial-strength searchlight. The searchlight radiates so much brightness that the firefly's faint glow becomes essentially undetectable, no matter how closely you look. This captures the fundamental obstacle astronomers face when attempting direct imaging. Stars are extraordinarily luminous compared to the planets orbiting them. A planet typically reflects or radiates only a tiny fraction of the light produced by its host star, making the task of photographing it directly comparable to trying to spot a lit candle positioned right beside the surface of the sun. The star's overwhelming glare simply drowns out everything nearby. This fundamental imbalance is why, for most of the history of astronomy, directly imaging exoplanets remained essentially unachievable, and why scientists instead relied on indirect detection techniques like the transit method described earlier. Overcoming this obstacle required an extremely specialized piece of technology known as a coronagraph. This device is integrated into one of the James Webb Space Telescope's key instruments, the mid-infrared instrument, often abbreviated as MIRI. In simple terms, a coronagraph functions like an incredibly precise light-blocking mechanism, comparable to covering a flashlight with your thumb so you can see what's positioned behind its glare. Except in this case, The thumb represents years of advanced optical engineering refined to an extraordinary degree. The specific coronagraph technology used here relies on what's called a 4-quadrant phase mask. This method divides incoming starlight into 4 distinct sections and applies a principle known as destructive interference, causing certain light waves to effectively cancel each other out. The result is a dramatic suppression of the star's overwhelming brightness, reducing it enough that the extremely faint light emitted by an orbiting planet potentially becomes visible. Even with this remarkable suppression capability, some residual starlight inevitably leaks through the system. No blocking mechanism achieves complete perfection. This is where sophisticated computational processing becomes essential. After Webb collected its initial raw observational data, a team of researchers led by astrophysicist Anne-Marie Lagrange, affiliated with France's National Center for Scientific Research in Paris, applied advanced algorithms designed to further eliminate any remaining traces of stellar contamination, methodically stripping away interference layer by layer. Once this meticulous cleanup process was complete, something previously invisible emerged clearly within the data. A faint but unmistakable infrared source positioned precisely in the gap between the first and second rings of the debris disk surrounding TWA7. This was exactly the location where scientists had theorized a hidden planet might be lurking, based purely on the structural pattern of the disk itself. Webb's initial observation of the TWA7 system took place in June 2024, and that first look immediately revealed the mysterious object sitting exactly where the gap in the disk was located. However, scientific rigor demanded more than a single observation before any conclusions could be drawn. Researchers needed to systematically rule out alternative explanations before confidently announcing a genuine planetary discovery. Before making any formal announcement, the research team had to eliminate other possible explanations for what they were observing. Could the faint infrared glow actually be an unrelated background galaxy that simply happened to align, purely by coincidence, with the gap in the debris disk? This kind of accidental alignment is a legitimate concern in astronomy, since deep space contains countless faint, distant objects capable of appearing in unexpected and misleading positions. To resolve this uncertainty, researchers calculated the statistical probability that the detected object was actually an unrelated background galaxy rather than a genuine planet. That calculation produced a probability of roughly 0.34%, well under half of 1%. In other words, the statistical evidence overwhelmingly supported the conclusion that this was indeed a real planet, not some coincidental alignment of unrelated objects. With this level of statistical confidence, the team felt ready to formally present their findings. Their research was subsequently published in the highly respected scientific journal Nature in late June 2025, and the announcement generated significant excitement throughout the global astronomy community. This wasn't simply another addition to the growing list of confirmed exoplanets. It represented something categorically different and historically significant. So what exactly is this newly discovered world? Based on the collected observational data, scientists estimate TWA7b's mass at approximately 100 times that of Earth, translating to roughly 0.3 times the mass of Jupiter. This places the planet in a mass category comparable to Saturn, classifying it firmly as a gas giant rather than a rocky, potentially habitable world. It's certainly not a destination anyone could ever physically visit or stand upon. What makes this particular mass figure so remarkable isn't simply the number itself, but its historical context within the field of direct imaging. Every single exoplanet ever successfully photographed before TWA7b was substantially heavier. The previous lightest directly imaged planet was approximately 10 times more massive than this newly discovered world. This single discovery, therefore, doesn't just add another entry to the catalog. It effectively opens up an entirely new, significantly lighter category of planets that astronomers can now realistically hope to observe directly. Regarding orbital distance, TWA7b sits roughly 50 times farther from its host star than Earth sits from our Sun. If you were to translate that same distance into our own solar system, the planet's position would land somewhere far beyond Neptune, out in the cold, dark outer reaches where sunlight barely reaches. Despite this extreme distance, the planet isn't quite as frigid as one might initially assume. Preliminary temperature estimates place it around 320 Kelvin, which converts to roughly 47 degrees Celsius, or approximately 117 degrees Fahrenheit. This relative warmth doesn't originate from its distant host star. Instead, it comes from the planet itself. Because TWA7b remains extremely young in astronomical terms, it continues radiating residual heat generated during its own formation process, essentially still glowing faintly from the energy released while it coalesced within the swirling dust and gas that once surrounded its parent star. Beyond simply representing an impressive photographic achievement, this discovery carries substantial scientific weight because of precisely where the planet was located. This marks the very first instance of a planet being directly observed sitting inside the gap of a debris disk, exactly matching the location theoretical models had long predicted. For years, astronomers have theorized that the distinctive ring structures and empty gaps commonly observed within dusty disks surrounding young stars are actively carved out by orbiting planets. As a planet moves through its orbit, its gravitational influence clears away nearby material, either absorbing dust and small particles directly or locking them into stable orbital patterns, ultimately producing a visible gap in the surrounding disk. This concept has long served as a foundational principle within planetary formation theory, yet it had never been directly confirmed through actual observation of a planet occupying one of these gaps. TWA7b changes that entirely. Its precise orbital position aligns almost perfectly with the gap detected in the debris disk surrounding its host star, matching closely with what theoretical models predicted a planet of this exact mass would require to produce such a structure. This represents far more than simply another planetary discovery. It constitutes direct observational evidence connecting long-standing theoretical predictions to physical reality, confirming a process astronomers had strongly suspected but never actually witnessed firsthand. There's an additional fascinating dimension to this discovery worth exploring further. Data collected by Webb suggests the possible presence of a small cluster of dust sharing TWA7b's exact orbital path around its host star. Within our own solar system, Jupiter has comparable companions known as Trojan asteroids, groups of rocky bodies that share Jupiter's orbital path, gravitationally locked into stable positions both ahead of and behind the planet itself. Should TWA7b possess a similar dust formation, sometimes described as a Trojan disk, it would represent the very first time such a phenomenon has ever been detected around a star other than our own sun. This alone would constitute a significant scientific finding, layered on top of an already historic discovery. Considered together, these combined findings accomplish far more than simply adding one more entry to the expanding catalog of known exoplanets. They provide validation for decades of accumulated theoretical work regarding planetary system formation, demonstrate the practical effectiveness of a powerful new observational technique, and hint at additional undiscovered structures that may exist around other young stars scattered throughout the galaxy. This single set of observations simultaneously touches upon multiple major open questions within planetary science, which helps explain why the astronomical community responded with such widespread enthusiasm. At first glance, TWA7b might not appear to be the most exciting object imaginable within our vast universe. It doesn't sit within its star's habitable zone. It's a frigid, distant gas giant rather than a rocky world capable of supporting life as we understand it. In many respects, it could be described as a fairly unremarkable planet occupying an equally unremarkable location. Yet its true significance lies not in what the planet itself represents, but rather in what its successful discovery proves is now genuinely achievable. For centuries, humanity's search for worlds beyond our own solar system depended entirely on indirect evidence and inference. Galileo's primitive telescope revealed moons orbiting Jupiter back in the early 1600s, fundamentally challenging the widespread assumption that everything in the heavens revolved around Earth. By the 1990s, astronomers had definitively confirmed that planets exist around stars other than our own. From that point forward, thousands of additional exoplanets were identified, but always indirectly, through subtle dimming patterns or minute gravitational wobbles, never through an actual direct look at the planet itself. What this latest observation successfully demonstrates is that direct imaging of planets falling within the same general size and mass range as those found in our own solar system is now genuinely achievable using current technology. This isn't merely detecting some massive object several times larger than Jupiter. It's successfully photographing something roughly comparable in scale to Saturn, a planet whose overall size is directly relatable to worlds we already understand intimately. Lead researcher Anne-Marie Lagrange has publicly discussed her long-term ambition of eventually applying similar imaging techniques to directly photograph genuinely Earth-like planets. This particular discovery represents a concrete, meaningful step toward achieving that ultimate goal, proving that the necessary instrumentation, computational methods, and overall observational strategy actually function exactly as intended in practice. Every future attempt at direct planetary imaging can now build upon lessons learned from this documented success, rather than proceeding purely from untested theoretical assumptions. Looking further into the future, astronomers anticipate that Webb will continue refining these techniques, gradually pushing toward detecting even smaller, less massive planets in the years ahead. However, truly Earth-like planets will likely require instrumentation even more powerful than what Webb currently offers. This is precisely where the extremely large telescope enters the picture, an enormous ground-based observatory currently under construction within Chile's Atacama Desert. Featuring a primary mirror spanning an impressive 39 meters, It's set to become the largest optical telescope ever constructed, specifically engineered to push the boundaries of direct imaging technology even further. Current projections suggest it will become fully operational around 2028. The combined capabilities of Webb operating from space alongside the extremely large telescope working from the ground could, within the coming decade, potentially provide humanity's very first direct photographs of genuinely habitable worlds. Planets similar enough to Earth that they might realistically support life. This recent discovery doesn't represent the final destination of that broader journey. Rather, it serves as concrete proof that the pathway forward is both real and navigable. There's something genuinely profound about this discovery that extends well beyond the pure scientific achievement involved. Consider, for a moment, what a photograph actually represents at its core. Light traveling from some distant source, entering a lens, and ultimately being captured and recorded. Every time you glance at a sunset or snap a picture of someone's face, you're essentially receiving light that has traveled some measurable distance before finally reaching your eyes or your camera's sensor. The infrared light captured within this particular image departed from TWA7b and traveled through the vast emptiness of space for a full 111 years before finally arriving at Webb's mirror. That light began its incredibly long journey well before the emergence of modern aviation, before telephones became commonplace household items, before much of the technology that now defines contemporary daily life had even been conceived. It crossed an almost incomprehensible stretch of cosmic distance, entered Webb's golden mirror, underwent careful processing to eliminate interference, and now exists as verified, permanent scientific data available for researchers to study for many generations to come. Throughout history, every time astronomy has gained access to a more powerful observational instrument, humanity's fundamental understanding of the universe has expanded dramatically as a direct result. When Galileo first pointed his rudimentary telescope skyward in the early 1600s, he discovered moons orbiting Jupiter, fundamentally undermining the long-held belief that everything in existence revolved around Earth. When Edwin Hubble utilized a powerful telescope at Mount Wilson during the 1920s, he definitively proved that fuzzy smudges previously assumed to be nearby gas clouds were actually entire separate galaxies, instantly and dramatically expanding humanity's understanding of the universe's true scale. When the Hubble Space Telescope launched in 1990, it subsequently revealed that seemingly empty patches of sky were, in reality, densely filled with thousands upon thousands of distant galaxies. The James Webb Space Telescope is now actively writing its own remarkable chapter within this same historical tradition. Launched on Christmas Day in 2021, it spent several months carefully unfolding its intricate mirror structure and cooling its sensitive instruments before finally releasing its first full-color scientific images in mid-2022. Images that immediately captivated both professional scientists and the general public alike, showcasing stellar nurseries, gravitationally distorted galaxy clusters, and the deepest, infrared view of the early universe ever successfully captured by any instrument. Since that initial release, Webb has continued steadily expanding the boundaries of what's scientifically possible. It has successfully detected carbon dioxide, water vapor, and methane within the atmospheres of numerous distant exoplanets. It has also closely examined a distant world designated K218b, uncovering chemical signatures that have sparked cautious yet genuinely exciting scientific discussion regarding potential biological origins. Though researchers consistently emphasize that entirely non-biological explanations remain equally plausible, and considerably further study will be required before any firm conclusions can reasonably be drawn. What fundamentally distinguishes this particular discovery from Webb's many other notable achievements is the underlying method itself. Rather than analyzing starlight that has passed through and been filtered by a planet's atmosphere during a transit event, Webb directly observed the planet's own emitted light, glowing faintly in infrared wavelengths, sitting precisely within its orbital position inside the surrounding debris disk. This distinction carries enormous practical significance, because the vast majority of planets never actually happen to pass directly between their host star and Earth from our particular vantage point, meaning the transit method simply cannot detect them at all. Direct imaging, by contrast, isn't constrained by this same fundamental limitation. Provided a planet is sufficiently bright and the available technology sufficiently sensitive, it can potentially be detected regardless of its specific position within its orbit. Somewhere within the continuous stream of data that Webb keeps collecting, additional undiscovered worlds are very likely waiting patiently to be found. This single, successful direct imaging achievement represents both a genuine milestone and a solid foundation for future work. Compelling proof that the necessary tools now truly exist to begin genuinely seeing, rather than merely inferring through indirect evidence, the countless other worlds scattered throughout our galaxy and beyond.